First off, this should all be familiar to you because this was the homework. The Celsius scale was named after Anders Celsius. His scale, it was a centigrade. What does centigrade mean? Someone tell me. Centigrade. It's in the word centi.
100, scale of 100.
100 equal divisions. And he based his endpoints on what?
Freezing.
Go, Sam.
The melting freezing point of water.
Melting point of water.
And boiling.
Melting and boiling point. Freezing and melting means the same thing. It just doesn't. Don't worry too much about that. All right, so that's what he based. Please stop talking. That's what he... Boys, thank you. Now, this is actually quite easy to get. What you do, you can get some water and you throw in some ice cubes, and they might be cold, like real cold, like come out of the freezer at minus 20 degrees Celsius. They're going to absorb some heat, and some will melt. But eventually what you get is, it's called the double point. The double point at 0 degrees Celsius, which is what he decided, that is where you have two states existing in the same beaker. So you can have water at 0 degrees and ice at 0 degrees. Now, I believe Mr. Angus has been lucky enough, or kind enough, to produce for us a double point. It's basically just a bucket of water and ice that's been sitting there for long enough that they are at the same temperature. So you can very easily make the double point. So that's what he did. He placed his thermometer into the beaker. All right. And obviously the contraction, blah, blah, blah. We learnt how thermometers operate. He called that 0 degrees. Then he went to another double point. And so this time you get a little bit of a flame underneath there, a bit of fire, you know, there's your beaker. And then you get bubbles of steam. And I'm attempting at I think I've got the double point occurring over in that urn. You can have liquid water at 100 degrees, and you can have gaseous water also at 100 degrees. Okay? So he placed his thermometer in. The alcohol expanded more, it went higher up, and he was able to put his two endpoints. Okay? And basically, he had a nice long glass thermometer, two endpoints. He says, you know what, I'm going to make 100 equal divisions from that top point to that bottom point, and that is my centigrade scale. Okay? Turn that down. We don't need the double point. But here's the problem. These 2 points can vary. If there is impurities in your water, bits of salt, bits of dissolved gases, bits of dust and snot and dirt, that can affect when it would melt or boil. Also, air pressure. The atmospheric pressure plays a big role on when water will boil and when it will freeze. So with pressure, let's go full screen on this. You might have heard this or read this somewhere, that at Mount Everest, the boiling point, there's such less air pressure because you're way up in the atmosphere. There's less gas above you when you're 8,000 meters above sea level. Water will actually boil at around 80 degrees. Okay? So imagine if you were trying to make a thermometer and you lived in, Nepal. When you do your melting point and your double points, I should say, your line's going to go up. You're going to mark a line, and if you call that 100, you could go down to sea level and put it in boiling water. It's going to go above that scale. So that was the problem. You cannot have a scale that's based on points that can change. We need to find some fixed points. They were later amended to these fixed points. Can anyone recall what they were? Because I think some of you mentioned them. Yep.
Absolute zero.
Absolute zero. We will discuss what absolute zero is in today's lesson. Now, we have a conversion. It comes out that this temperature is minus 273.149 degrees Celsius. Pretty cold. And the other one, does anyone remember the other one? Yes.
5.01 degrees.
It is but it's got a name. Triple point. Please stop talking.
Isn't it? Yeah.
And it's 0.01 degrees Celsius. For some strange reason, just a little bit above 0 degrees. Okay? All right. So, and in fact, it's of this very specially purified water. So there's a technique to try and remove out as much impurities. You want a pure substance of water. In chemistry, a pure substance, every single particle in your collection is identical. You don't want any dissolved oxygen. You don't want any dissolved nitrogen. No CO2, no salt, no ions. So there's a process to try and do that. If you put a fish in that water, it would die because there's no dissolved oxygen. Fish need oxygen in the water. They need a mixture. We need a pure substance. Now here's the key thing. These 2 points are physical constants. Big important word, constant. They will never change. So you could go to the other side of the universe and find a couple of molecules of oxygen and hydrogen, call it water, and under the same conditions, it will always occur at this temperature. You will get the triple point. At absolute zero, again, that is the lowest temperature possible. We will explain these two right now. So, the triple point's pretty cool, and I've got some videos loaded up. Thermodynamic. Now, what I want you to imagine is that, remember I said if we lower the pressure, the boiling point will actually drop to 80 degrees. If we're on Mount Everest, we've now got a range of 80 degrees between melting and boiling. All right, and remember we can have double points. Melting would be solid and liquid. Up there would be liquid and gas. What if we went higher up? Let's reduce the pressure. Then we find that the boiling point drops, gets closer and closer and closer. And eventually, at just the right pressure, these 2 points exist at the same point. And then your 2 double points meet together, you have the triple point. You can have all 3 states of matter existing in the same substance. We will never see it in this classroom at 1 atmosphere. It's separated by about 100 degrees. But in a vacuum chamber, I'll just mute this. All right. Now, what you cannot see is that they're currently pumping all of the air out. Oh, just started boiling. They're currently pumping all of the air out of this vacuum, out of this flask. Okay. They're also trying to reduce the temperature to 0.01 degrees, as well as the pressure. I believe it's something like 0.06 atmospheres. So it's quite difficult to get.
Would it be hot?
But you can, hang on, at the moment, no, it would be cold. It's getting down to 0. If you held it, it would be cold. Now, when it was bubbling, that was a double point. We had liquid and gas. But now let's see if we can watch. You might see a crystallization site. There it is. We've got solid water. Well, it's actually tetrabutyl alcohol, but pretend it's water. Solid and bubbles and liquid. So it is boiling and freezing at exactly the same time, at exactly the same temperature. Isn't that weird? How can it do that? It's in a vacuum. So I might be able to show, thanks Kylie, well, all right. I might be able to show you, here's another video. I will just mute it. We don't need to listen to this bloke. Oh, I didn't mean to do that either. I'm trying to go full screen on this bad boy. These marbles, this is scratched. It's marbles that have scratched glass. What that does, it produces what's called a nucleation site. For a crystal to occur, it needs somewhere to start. And so if you've got pure water, it will never start. And so if you have a little scratch, a crystal can start growing, and then that's how your ice crystal can form. Okay? So that's just helping the ice move along. The problem is with nice plastic Petri dishes, if they're new, then, oh, what just happened? It froze. All right. So we're at a double point. But now we need to get little bubbles of vapor. There they are. Or maybe bubble, bubble, bubble. Okay? So again, this is water in a vacuum. You might see that big bell jar. Oh, let's just go back. Forward. I'm getting impatient. There it is, bubbling and freezing away. This is the vacuum, this is the big bell jar, and there's a pump that's basically sucking all the air out. Now, the pressure goes up. He's just released the valve, and so the pressure's rising. All of the air would be being pushed in. Okay? The vapor stops, and then you're back to the double point. Now, these videos, gentlemen, that I'm showing you today, they are all... It's not letting me get out of... They are all at the top of the page. So if you go to the top of the page, all of the links that I show you are right here. Okay, so you can go and watch them. They go for 3 minutes, 8 minutes, etc., but you can do that in your own time. Now, let's just quickly look at the Fahrenheit scale. But all I want you to know is that it's a silly scale, it's imperial, and it's silly, and we can laugh at it. Daniel Gabriel Fahrenheit, German physicist, he took his thermometer, stuck it in his armpit, it got to a certain height, he said, let's call that 100. And then he goes, all right, let's try and get the coldest reproducible temperature, which is a saturated solution of ammonium chloride. You take this salt, ammonium chloride, white powder, you throw it into some water, you stir it around, and as cold as it gets, lock that off, call that 0. Well, we actually got it at about minus 20 degrees Celsius. He called that 0. So he had these two scales, body temperature and the coldest temperature you could get by dissolving salt into water. We do have the conversion. We don't want to spend too much time on it. It won't be in the test. But what have we got? We're going to have degrees Celsius is F take 32, divide it by 1.8, which is the same as timesing it by 5/9. And Fahrenheit is going to be degrees Celsius times by 9/5, and then add 32.
Why is it like 509, 905?
Yeah, so he didn't have a centigrade scale. What he did was he split his by 90. Hang on, is it written there somewhere?
98.26. Defining 96.
96, 2 to the 6th power above the freezing point. So he didn't use 100. His is not a centigrade scale. If his was a centigrade scale, then it would be a nicer conversion. But he went, I'm going to go in divisions of 2 to the power of 6. Again, it's weird, it's not good, we don't use it. Let's get over to an important one. The Kelvin scale. William Thomson, 1st Baron von Kelvin, he was a British mathematician and an engineer. Now, here is what he did. He used a very clever relationship between temperature, pressure, and volume. Now, I'm going to very quickly demonstrate this, but not really. Here we have a sealed steel bowl. So there's it's got some air inside, or a gas inside there, all right? And there's a pressure gauge, which is measuring how many particles are bashing the bottom of this gauge and with how much force. So we spoke about how things expand. When they gain energy, they travel faster, they collide with their walls of the container with more force. They're basically going to exert more pressure. Now, I can very quickly show you this. Here we go. Abracadabra. Here is my pressure. If I place him in the hot water, the pressure goes up. That makes sense with our kinetic theory of matter. Now the air molecules have gained energy, they've got a higher temperature, they're bashing into the walls of their container with more momentum, more force, and so the pressure rises. Okay? And then if we go the other way, let's take some energy away from these atoms. Look, now the pressure is dropping because we're removing some energy from them. Their temperature is going down. They're bashing the walls of their container with less. Good. All right? And so we can get, here's the good thing. There is a direct relationship between temperature and pressure. If I doubled the temperature difference, I would double the pressure difference. And so Lord William von Baron I Kelvin used this very clever relationship to do something cool. Pardon the pun. So, here's my little steel bulb with my pressure gauge. Let's put him in some hot water. Okay. That's a Bunsen burner. And then let's place it in some ice cubes. And obviously the pressure goes down. Now you have a nice space here to make a lovely set of axes. Whoa. Actually, I'm going to put my axes over here. And we'll have pressure. It doesn't matter what units we put our pressure in. Let's go kilopascals. That's, I can't really write that small. Kilopascals, K, capital P, lowercase a. And let's go temperature. Okay? Now what he did is he got his volume and he placed it in various temperatures. He could put it in an oven. He could put it in boiling water. He could put it in room temperature water. Maybe get some ice, put it in some ice water. And what he discovered is that all of these dots, now I'm going to cheat. The reason I'm going to cheat is because you can cheat as well if you want to put your ruler. All of these dots, no matter how he varied the temperature, all of those dots were linear. All right? And you know, he might have gotten down to maybe, let's say, 20 degrees. And then maybe he got up as hot as, I don't know, 300 degrees. So he had his data. Yes? Huh? Blow, yeah, go for it. Now, what he goes, all right, perfectly linear data. Get that down. Now, back in the 1800s, it was pretty difficult to get much colder than 0. They didn't have refrigeration. They might have been able to expand some gas and get down to minus 50 or minus 40, but let's just say this is the range, okay? Now, he goes, but look at that. That is a linear relationship. So I could extrapolate. I could draw in my line of best fit. And I would like to change to a thin red line. Thank you. And the line appears to go back to this point here. This was the lowest possible theoretical temperature. What it means, at this temperature, there is 0 pressure. That is the pressure at which the particles are not even colliding with the walls of their container. That must mean that they are not moving. So that is the temperature at which atoms cease to jiggle. That is the temperature that they have no velocity, and that is the lowest possible temperature ever. So, could we please write, and I'll get rid of the ruler for now, could we please write down here, he got minus 273.149 degrees Celsius. He was actually using Celsius's scale. And so his temperature scale on the x-axis was degrees Celsius. So he goes, you know what? If this is the lowest temperature possible, let's call that 0. Let's start at 0 and then work our way up. Why would you start at 0 Celsius and go into negatives? So he's going to call that 0 Kelvin. Okay? We'll write it here, 0 Kelvin.
Is there any way to get below that?
No, because that is when a substance has 0 internal energy, no potential energy, no kinetic energy, no energy at all, and so it's not possible to have negative energy. It's not a real thing. And the cool thing is, he basically did this with lots of different gases, with different volumes and different temperatures, and no matter the data he got. You can see what I'm doing here. Every data he got all pointed back to the same point, right? And that just made his idea more reliable. So, could we please write, again, if you have the room here, 2 × 10⁻⁻⁷ I'll just go a little bit. It is a theoretical temperature at which all movement ceases to exist. All movement stops.
Why is it theoretical if it's true?
Well, I'll tell you in just a moment.
Will it ever be
No, can't go colder than that. Okay?
like ever?
Nope, never. Please get this written down. I've got some more cool videos to show you. Get this written down, please.
Then how hot can it go?
Get this written down and I will attempt to answer all these questions. I'm just moving this around a little bit. My bracket goes down there. Alright, so it's a theoretical because there's another law in physics. It's called Heisenberg's uncertainty principle. Basically, you cannot know, we're talking about an atom, an electron, the tiniest subatomic particles. You cannot know its momentum, its speed, and its position at the same time. When you get down to really, really small, things get really weird and you get quantum physics occurring. So, an electron as well is not allowed to stop. Because if you could stop an electron, I could say, right, I know your speed and I know your position. They're not really allowed to stop. So remember, electrons are quite light. They don't have much mass in an atom. They have to basically keep spinning. Scientists have gotten down to within about 1 million or 100 million of a Kelvin. 100 million is 8 zeros. So they have gotten temperatures as cold as 0.0000001 Kelvin. Which, if we use our conversion, it's minus 273.149000001 degrees Celsius.
But they've never
Sorry.
done that.
149,99999 degrees Celsius. They have never gotten there, but they've gotten damn close. Okay?
Put it in the freezer.
Alright, so because Kelvin used, this is why it's a nice conversion. Because he was using the Celsius scale, it has the same scale step. So what I want you to write here is an increase in 10 degrees Celsius is an increase in 10 Kelvin. Okay? What that means is if your change in temperature is 10 degrees Celsius, then your change in temperature is 10 Kelvin.
How come you don't say degrees Kelvin?
Yeah, I don't, well,
What's that little thing? What's that symbol?
delta, delta means change in. It's a Greek capital delta, a capital D in Greek is delta. It means the change in. But here's the thing, it's the scale, it's the step, it's the change is the same. You cannot say that 10 Kelvin is 10 degrees. But if we increase both of them by 1, their scale step is the same. So please, students will still make this mistake no matter how many times I say it. 1 degree Celsius does not equal 1 Kelvin. It's a change in 1 degree is a change in 1 Kelvin. So here's our conversion, and we want to use this in our classes. We might be asked to do this in our tests. We've got Kelvin equals degrees Celsius plus 273.1499, but we'll just leave it at three values. And going the other way, degrees Celsius is Kelvin minus 273. All right, so we need to use this.
Oh, so they just start at different points.
Yep.
But when they increase it, both.
Yep, because when Kelvin was doing his experiment, he was using a Celsius thermometer. And so when he was changing his temperature, he was measuring the change in Celsius.
Use Fahrenheit.
So basically he said, well, I'm gonna take my Celsius scale and find where can we start at 0. There, 0 Kelvin. All right, so that's why it's called an absolute scale, because you cannot get any lower than 0 Kelvin. You can't get negative Kelvin. All right, but we can get negative 100 degrees. So in this room right now, we're at about 298 Kelvin. That's just 25 degrees. When I heated my beaker up to boiling, we got up to 373 Kelvin. In here, it's at about 273 Kelvin. We could say the range between freezing and boiling is 100 Kelvin. We could say it's 100 degrees Celsius. Okay? I like this because remember, this might be at 0 degrees Celsius, right? But if you went to Antarctica where it was minus 80 degrees Celsius, this bucket is 80 degrees warmer than the coldest recorded temperature on Earth. You could come up and hug this bucket of water like it was a hot water bottle if you were in Antarctica where it got down to minus 80 degrees. So I want you to appreciate that at 0 degrees Celsius, you can still get energy out of it. Yeah? If I put something that was colder than 0, then the energy would come out of the ice and go into the colder object. So just appreciate that there's still a lot of thermal energy in ice. It's just that we as warm-blooded creatures we're always above 0, right? We're 37 degrees, the room's 25, and we always consider that lump of ice as cold. But if you were on the dark side of the moon, where it gets down to like 10 Kelvin or minus 263 degrees Celsius, a lump of ice would be a nice warm toasty rock that you could go and get all of the energy out of. Yes?
In a vacuum, you have temperature if there's no particles.
That's the problem. Temperature is a measure of how fast particles are jiggling. And so if there are no particles to jiggle, how do you measure temperature? Weird stuff occurs in vacuums, and I've got a video loaded up to show you weird stuff. Also, weird stuff happens when you get down to these really, really cold temperatures. Because everything's jiggling. It's chaotic. The atoms in your body are jiggling. The atoms in the table, the atoms in this stapler are jiggling backwards and forwards. It's quite chaotic. So when we get down to very little jiggle and we get rid of all that chaos, some really weird phenomena occurs. We don't normally see it because we hardly ever get down to these temperatures. But in recent times, 1940s and 50s and 60s to now, we've been able to get down to that cold. You can get this really cool thing called superconductivity, where there is no electrical resistance, and you can get levitation. You can get some cool stuff happening. Let's watch some videos because I have spoken for enough.
So we have one suspended, super strong, neodymium magnetic Mobius strip track. All we need now is some liquid nitrogen. So we're down in one of the labs at the RI. This is where the liquid nitrogen is stored.
Now, what they did, a Mobius strip is just a loop that has one surface, one side, and he's coated it with magnets. Now, this little pellet here, this is called a superconductor, and underneath this certain temperature, it turns into a superconductor where it can observe quantum levitation. Now, all materials will do this at absolute 0. In the very early 1940s, they found some metals would do it at about 3 Kelvin, so minus 270 degrees. And then they tried to find, well, how warm can we get? Can we get warmer and warmer and warmer? This little pellet here, it's an alloy of yttrium, barium, and copper and oxygen. And it's quite expensive. And it will do it at about minus 150 degrees, I believe. Look at that. It's levitating above the magnet. And so this will do it. what he got out of that big flask was liquid nitrogen. Liquid nitrogen is colder than minus 150 degrees. So he just placed that pellet in the liquid nitrogen, and all the energy came out of that pellet. It got down below this temperature point, and it gets locked into a magnetic field. That's how we can get quantum levitation. Now he's just going into a science explanation here. Don't worry about that. So what he's done, have a look. Now once it gets warm, it loses that effect. So it actually got too hot and it fell onto the track. So what he's got here is a little boat. At the bottom of the boat is the pellet, and inside the boat is just a little vessel that he can pour liquid nitrogen into. And so if the liquid nitrogen can sit in that insulated boat, there we go, then it can stay cold. So you're going to take the cryo, the freezing, the cooling effect, you're going to take it with you. Okay. And so away it goes around the Mobius strip, so it goes around on the bottom and then it goes around on the top.
How is it flipping over? What?
Because it's a Mobius strip.
You take, it's like take a tape of paper, flip one side and connect it, and it's called a Mobius strip. It's a very special geometric shape that only has
If you
one.
try to draw around it with a pen, if you get a paper one, you try to draw around it with a pencil, you don't have to take your pencil off the paper.
Exactly, because after one turn you've flipped over and you're on the other side. Mitchell is doing so now. Well done, Mitchell. All right, now, and it's upside down. The thing is, he had to lock it in situ. So when he wanted it to lock into the magnetic field, he had to cool it below that temperature in the presence of the track. That's why you might have seen a part of the track was on the bench, and he pours in the liquid nitrogen and it locks in. If you didn't lock it in and you just got it cold and you brought it over, nothing would happen. The field lines had to be inside the pellet. Now, hang on. In 1988, I think, Back to the Future had their first hit with Michael J. Fox, and they went to the future, and the future was 2016. And they went into the future, which for them was 30 years in the future. And in 2016, there was a hoverboard. It was this big purple magenta hoverboard that Marty McFly was able to zip around in the future on. A hoverboard. And as that time got closer and closer, all of the fans of sci-fi said, right, 2016's approaching, where the hell's my hoverboard? And that became a bit of an internet meme. There was a company called Lexus who tried their darndest to make a hoverboard. So let's just watch this. It goes for 5 minutes and we have the time, I think. So let's do we put the sound back on? The sound, no.
Is this like Lexus the car company?
Yeah. All right.
We at Lexus always try to achieve the impossible. That is the attitude we apply to everything, with a constant desire to do what has never been done before.
It's like old stories, old fairy tales, the flying corbett. And this is something close to that flying corbett.
Looks very unstable going.
It wants to go, doesn't it?
Making a hoverboard isn't a straightforward process. We have had quite few ups and downs because it's normal when you are trying to do something truly innovative.
The system doesn't need electricity at all. We just use the superconducting material. We use a permanent magnet and we use the liquid nitrogen to cool down the superconductor. So you just have to keep it cold to have a long hovering effect.
The magnetic track has a certain magnetic field configuration, and this configuration is now also present in the superconductor. And when they are cooled down, then this field configuration is frozen in. When the superconductor stays in this position, it's an art of material science.
When I came in, I think it wasn't going in the direction everyone wanted it to go. But when I seen it, I was well excited about it. I was like, I want to have a go. Let's see what it is capable of. Yeah, within a week, we'd progressed loads. We'd gone from just going 5 meters in a straight line to going around the corner as fast as we could. And then we started setting up the jump and making it higher and making the gap bigger. And we progressed quick, really quick.
Some of the design elements like the spindle grille and also the bamboo deck of the board, we're almost exactly replicating what's inside the Lexus car. There's the science part of it, and then there's the design and the beautiful part of it where we get to make it look amazing.
They put out a bit of a teaser with the Back to the Future, and then they put out an actual commercial of the hoverboard at this skate park. You can find that video, and so if you just YouTube search Lexus hoverboard commercial, this then came out. Obviously, this is the behind the scenes of that commercial. So in that commercial, it just looked like a bloke that just rocked up to a skate park with his hoverboard, and he's hovering around the skate park doing whatever he wants. But this was the trick. This was
The feeling of literally no friction and floating on air. It's hard to describe what that really feels like, man, but it's kind of like a science in yourself, in it. You know, you start to break it down. It starts to become less scary and less daunting, more fun. I started skating when I was about 7 or 8. It literally feels like I'm starting all over again from the beginning. Now, I'm really was born again, and then look, here's a skateboard, learn it.
basically built the track, and they built the skate park over the top of the track. So you see how it's just under that track.
Superconductivity is a fascinating phenomenon. It's spectacular, but it's complicated.
If we would have known at the beginning what would result at the end, we probably would have said, no, it's impossible. So you have to have dreams. Maybe they will not come true, but it's the direction you work.
As our legendary Takumi craftsman say, the difficult takes time. The impossible just takes a little longer.
So, the question was, why don't you just throw magnets down everywhere, go wherever you want? There's a problem with magnetic field lines. They can travel and they can be close together, but they can never intersect. So all you could do is make one path that could loop back on itself, but it could never intersect. You might be able to sort of go over it, but...
What about like train lines?
Well, it's the same with a train line. Oh, you mean to like switch over? Like their little...
Yeah.
I don't know. Maybe in the future they will. But at the moment, you cannot have a bloke on a hoverboard going this way and a bloke on a hoverboard going that way, unless you had some kind of magnets that could quickly change orientations. But then, you've seen trains crashing. You'd have hoverboards crashing. Anyway, let's get back to... That was just one weird thing. Now, don't pack away. I think people are packing up. This is called the Meissner effect, quantum levitation. At the moment, the warmest superconductor, I think, is minus 93 degrees Celsius. It is warm, minus 93. But still, that's 180 Kelvin. Still, we need it. The end goal of this investigation and technology and science is to try and find a superconductor at room temperature. But the problem with at room temperature, there's going to be too much jiggling of your materials. So they're trying to find materials that don't jiggle. So they're just investigating different alloys, different materials, trying to make different substances that aren't affected by all that chaos of temperature. So at the moment, minus 93 degrees. You can get down there with cryostats and liquid nitrogen, but you wouldn't be able to do it in this classroom. Have a think. If you could have a room temperature superconductor, the easiest thing I can think of is you could just point your car down the freeway and you could glide along without burning any fuel. You would save billions and billions of dollars a year not having to have a combustion engine. I don't know, a brake, electromagnetic braking.
They do that in,
The other one is
at work.
your computers get really, really hot when they try and play games. The graphics cards, the motherboards, the GPUs, they get phenomenally hot because of electrical resistance. If your computer could be made of a superconductor, there would be no electrical resistance, there would be no heat. You could basically power your 4K 60 FPS gaming rig with a tiny little AAA battery, and there would be no heat loss. So there's a lot of applications in this area, but I just want us to go back now to